Okay, so good morning and welcome back to Classical Mechanics 1 at CMI. Today is 7th of December, Tuesday, and we are on our 21st meeting. So before we continue, are there any questions? I had a few remarks about a couple of problems. I will go over that. But before that, any questions? Okay, I presume the previous lecture ended a little bit late, perhaps. Okay, so let me share my screen. Okay, I just had a few brief remarks about a couple of problems from the homework. One of them concerns question, 1 minute. I think I need to. Yeah, so question 4 from problem set 4. This concerned the simple harmonic oscillator in one dimension. And the equation of motion was mx double dot is equal to minus kx. I mean, many of you have written it in with the vector symbols, x hats, and so on. But at the end of the day, it is really in one dimension. So there is only one dynamical variable x of t. And one can write it in this simple manner. But it's okay if you have added x hats. And then one comment I want to make is that it was asked to write. So this first part was simply to write the equation of motion. This is what we mean by that. This is Newton's equation of motion. I mean, it is second order. That is Newton's formulation. Then we asked to write it in, write it as a pair of first order equations. Yeah. Now, I want to emphasize that in writing equations of motion, there is no need to try to solve the equation of motion. We are not asking that you deduce that x is a sinusoidal function of time or anything of that sort. That would count as solve the equation of motion. So many of you have tried to solve this equation of motion or to try to derive a conserved energy multiplied by integrating factor, try to integrate. All of that is not necessary. We're just asking for the equation of motion. And then we asked to write it as a pair of first order equations for x and p. So that is simply to say, recall that p is equal to mx dot. So to turning that around, you simply say that x dot is equal to p upon m. And the other equation then says that the rate of change of momentum is the force. Yeah, so this is the second equation, p dot is equal to minus kx. There is no need to solve the equation of motion and then find what p dot is. This is coming directly from Newton's original equation. Then we write it in matrix form because this is a pair of linear equations. P and x both appear to first power. Therefore, we define the column vector x comma p. Then its time derivative is given by p upon m and minus kx. We notice that this can be written as a 2 by 2 matrix times x comma p. Yeah, we maintain the same order, xp here, xp there. and since this is P upon M, there is no multiplication by X. There is only a multiplication of 1 upon M by P. The second row, you have P dot, and that's minus Kx. So here there has to be a minus K and then a 0 here. So this is the coefficient matrix A. That is how you identify it. There is no need to solve the equation of motion. This is something that many of you have tried to do. It is not necessary at all. Because there are many systems where you cannot solve the equation of motion in any simple way, but you can still write it in first order form and things of that sort. So it is important to distinguish and disentangle the problem of solving the equation and writing the equation in a particular way. And then we proceed to compute a squared and a cubed and so on, and even powers and odd powers. So most of you have been able to do that once you get the right matrix A. Any question about this matter? Okay. If not, so these are, I emphasize these are first order equations, first order in time, whereas the original equation was second order in time. So that is the main difference. We have gone from 1 second order equation to 2 first order equations. That is something worth remembering. Okay, then I had a brief comment on, let me take up another question. Question 2 from problem set 5. This had to do with the Galilean boosts. Yeah, and we were told that you have two events, A and B, which in inertial frame S occur at some time TA and some location R0, location with coordinate R0, and the other event occurs at TB, but at the same location, same coordinate R0. But TB is, let us say, more, or let us say TB is more than TA. Yeah, so they are at distinct times. Yeah, so these two events could be the two events where I raise my hand today sitting on this chair, and on Thursday I shut my eyes on Thursday. So these are the two events. They occur at the same place with respect to the frame of the Earth. That's very important. We are saying in a certain frame, they occur at a particular location. So with respect to that frame, we choose in this case the frame of the Earth, of this room. Yes. So in that frame, they occur at the same location, that is R0, the same coordinates as well. Now we want to view the events from frame S prime that moves at velocity v relative to S. Yeah. So we are making a so-called Galilean boost to a different frame. Now this frame may be the frame of a car that is moving on the old Mahabalipuram road at a constant speed. Yeah. And we are asking relative to that new frame, do A and B events occur at the same location? Yeah, and to be a little bit more clear, do they occur at the same coordinate, spatial coordinates? Yeah, in S prime, that is the question. The answer is emphatically no. They don't occur at the same location as per the observer in the moving frame. We have a way to change coordinates. Yeah, and that is R prime in the new frame is R minus Vt, where V is the speed relative velocity. And therefore, R prime A is equal to R naught minus VTA, while R prime B is R naught minus VTB. Okay, so I am computing the coordinates of these two events, the spatial coordinates of these two events. They are the same location, same coordinate in the original frame, but in the new frame, the coordinates are different because TA is not equal to TB. So according um, to the moving observer, they don't occur at the same location. Yeah, I hope this is clear. One could also think about it in terms of a train. Let's say it in a much simpler way in terms of a train. Yeah, in a train, I'm sitting inside a train. And in the frame of the train's carriage, I open my mouth, and then after some time, I shut my mouth. These are the two events. They occur at distinct times, but they occur at the same location with respect to the train's carriage. On the other hand, relative to an observer on the side of the train, on the train tracks or in the station outside, these two events will occur at different times. And during that time, the train itself has moved. So according to the observer in the station, the time when I open my mouth, I am located close to that person perhaps. And then when I shut my mouth, the train has moved away, and that's at a different location according to the stationary observer on the train tracks or on the station. Yeah. So so this is the difference. When we say location, we are implicitly having in mind a particular frame. If you change the frame, the concept of location can change. I hope this aspect is clarified now for those who had any confusion or question about it. Any further clarification about this? Okay, if not, let me go to one more question. I mean, there are several questions, but I just want to highlight two or three, and probably will address others at other time. Let me go to question 3 of problem set 6. Yeah, question 3 of problem set 6. And this was concerning a particle mass m in potential V of R. Yeah, and we were asked to find an integrating factor or use an appropriate integrating factor to derive a conserved energy. Yeah, this was the question. And many of you have got it right, but there are also some confusions. So first, let us write the equation of motion. If I write it in vector notation, it will be mr double dot is equal to minus gradient of v. Yeah, this is the vector notation equation of motion. In component form, this would say m, let us say x1 double dot is equal to, okay, let me put it down below, x1 double dot is equal to minus dv by dx1. So, I mean, I'm thinking of x1, x2, x3 as the three Cartesian components of the position coordinate. So you will have three equations, mx2 double dot is equal to minus dv by dx2, and mx3 double dot is equal to minus dv by dx3. Now, clearly there are three equations, so you need to do something to each of them. We may, of course, write them in a single line as mxi double dot is equal to minus dv by dxi. We are free to write it that way, where I runs from 1 to 3. Yeah. Now, the integrating factor that works in this case is to take the dot product with the velocity vector, which is r dot. Okay, so in vector form, what would happen? You would get m r double dot dot r dot is equal to minus gradient v of r times r dot, dotted with r dot. Yeah. And now you notice, if you are comfortable with vector notation, you could proceed from here and notice that this is d by dt of r dot squared. Well, m is there and a half. Yeah. So if you differentiate this, you will get that. But if you are not comfortable with that, or first time you want to work in component form, what you would do is take this equation, multiply by xi dot, xi double dot, and the process of taking a dot product means you must sum over. After all, dot product means r double dot dot r dot means x1 double dot times x1 dot plus x2 double dot times x2 dot plus x3 double dot times x3 dot, right? So you're supposed to add them up. So we must put a sum from 1 to 3. This is what it means to take the dot product, but if you write it in component form, and on the right hand side, you will have minus dv by dxi times dxi by dt, again sum over I running from 1 to 3. So it is very important to recognize that there is a sum involved over here. Okay. Yeah. Okay, we are still short of some students. Yeah, I hope everybody will join soon. Yeah, okay. So let me complete this brief discussion. So now it is easy, bearing in mind that there is a sum, this can be viewed as d by dt of half m xi dot squared, where again there is a sum over I, 1 to 3. It's very important to realize that there is a sum. And on the other hand, the right hand side can be regarded as d by dt of v. Because if you take the derivative with respect to time of v, you have to use a chain rule in 3 variable calculus, and that involves partial differentiation times derivative of x with respect to time, but you have to do it for each of the 3 variables that v depends on, namely x1, x2, and x3. Yeah. So combining these two, you will conclude that d by dt of half m xi dot squared sum over I and 1 to 3 plus v of x of t is equal to 0. Yeah, so now you have your conserved energy, and one could do the same thing in vector notation as well. Yeah, one remark for those who would like to, but one must say this. There is a convention in physics that repeated indices like the I over here or the I over here, a repeated index in a term is considered to be summed, and if you are going to use that convention, then this summation sign can be omitted, but you need to say so. Yeah. So one often writes this equation in succinct form as m xi double dot xi dot, yeah, where sum over I equal to 1, 2, 3 is understood. Yeah, so repeated index I is summed. Yeah, so that is, the summation sign is suppressed, but it is to be understood. But one has to say that. Okay, and any question about this approach?
Actually,
yeah.
Yes, sir. Like, actually, I had a question about the previous question. Like the
Sure. Yeah, you mean okay, the Galilean boost?
Yes, sir. Yes, sir.
Yes, please.
Sir, actually, in the lecture notes, it's given that like the instantaneous location of a particle is same no matter which coordinate system we use.
Yeah, that is true. That is in a particular frame. Yeah. So at that time, okay, you are right. You are right. And we are moving on from first standard to second standard. So I apologize, and no, I must say that I appreciate the the dedication with which you have read the lecture notes and absorbed it in an excellent manner. And I apologize for now moving to second class, where there I didn't say so explicitly, but the location depends on a frame. So in that context, we were talking about the location of Shakti Chauhan's house in the frame of the earth. Yeah, that was the context. And we did say that that location has an invariant meaning, though you may choose to use latitude, longitude, or some other coordinate system, or some Cartesian coordinate system, or some other coordinate system to give an address to the house. That was the sense in which we said location is the same, independent of the choice of coordinate system. But what I perhaps should have said, but did not say so explicitly, that the location does depend on the choice of a frame in the very basic sense. And that is where you have caught me here. Now we are changing frames. Now the location is not frame independent, yeah, if times are distinct. Is that okay?
Yes, sir. Yes, sir.
Okay, so yeah, you have my partial apologies, but I think in the process you have also learned something very useful. I hope so, at least.
Yes, sir. Yes.
Okay, good. Yeah, yeah, I understand why you have raised this question, and it's a good one. So yeah, we have learned something good here. There is a concept of a frame, and there can be different coordinate systems within a frame. Right, so these are an additional level or layer of detail within the frame of the Earth. We can choose latitude, longitude. We can choose co-latitude, longitude. We can choose Mercator projection. We can choose various mapping systems and change coordinates between them, all of which are in the same frame. Now we are doing something different. We're changing the frame itself. Okay. Yeah, so good question. Anything else that I can address about this matter? Okay, but I think the person sitting in the train example is very nice. It makes it very explicit. If I open my mouth and then shut it after some time, I may have moved during that intervening duration, and a person in the railway station will not say that I am at the same location, at least in any reasonable sense, if the train is moving. Okay, now there was one more question last time from, let me try to remember, Shubham Kumar. This concerned the our derivation of Newton's law of gravitation. So, and it was a pertinent question. We used Kepler's third law, and the idea of Newton's second law of this reciprocity to come to the conclusion that the force felt by the Earth due to the Sun is proportional to the product of the two masses. And the masses here that came in really entered from the inertial mass that appeared in the mass times acceleration formula. Yeah. So according to the question raised by Shubham Kumar, these masses should really be the inertial masses of the bodies. So then what is all this mumbo jumbo about gravitational masses? There is no such thing. And that point is well taken. Now, I should clarify that the assumption that gravitational and inertial masses are the same has sort of already crept into this argument, because we have used a very strong experimental result that Kepler's constant is independent of the planet. Yeah, so the Kepler constant appeared here, and that played a very important role in this deduction. We said that since K is independent of the mass, independent of the planet, so it doesn't depend on the color of the planet, it doesn't depend on the composition of the planet, leave alone its mass or any other property. Yeah, and that is why we said that this force formula is proportional to the inertial mass of the Earth. But so in other words, we have used some experimental information to come to this conclusion. In fact, Kepler's constant is not a constant. It does depend on planet weakly. And so one could imagine that the dependence on planet can be encoded through some property of the planet, which you would call the gravitational mass. Okay, so if one were to do it more carefully, there is scope for allowing for that dependence. And then you would want to check carefully, are the two really the same or not, and so on. Now, it turns out that the dependence of Kepler's constant on the planet is not because the gravitational inertial masses are different, but because of some other factors that we have ignored. I mean, we have ignored the fact that there are various things we have ignored. We have treated them like point particles. We have ignored the fact that the center of mass of the system is not really at the center of the sun. There are many approximations we have made, which can be used to explain why this K is not exactly planet independent. And that essentially accounts for all of those things. So this is the issue that, in brief, that in answer to Shubham's question. So let me just read what I had written in the notes. It's also mentioned in the video, in the caption to the video from last lecture. So in this derivation of Newton's law of gravitation, me was the inertial mass of the Earth, since it came from the mass times acceleration term in Newton's second law. Now, by Newton's third law argument, ms would then have to be the inertial mass of the sun. Yeah. So one may wonder where there is room for gravitational masses that may be distinct from inertial masses in Newton's law of gravity. So this was the question posed. So this apparent lack of room is because we assumed that Kepler's constant K is independent of the planet. This is very analogous to Galileo's assertion that all bodies fall in the same way when dropped from a common height above the Earth's surface. So Kepler's law saying that the motion of, the 2/3 law is t squared proportional to r cube law is the same constant of proportionality for all planets, is very analogous to Galileo saying that all bodies, whether a ball or a body or a bottle of water, no matter how they look, how they feel, etc., when dropped from the same height above the Earth, accelerate in the same manner. So if K dependent on the planet, then that dependence could be encoded in a property that would in effect lead to a gravitational mass that is distinct from the inertial mass. So that is where we have gotten around this. And in fact, K is not exactly the same for all planets, but its dependence on planet can be explained by other effects that we have ignored. Okay, so this quickly is where the possibility of the difference between gravitational and inertial masses could enter in Newton's law of gravity. Yes, please.
Could you repeat the last point about how they could be different? Because till now I didn't understand what the difference between gravitational and inertial was.
Yeah. Okay. So let me try to do that more slowly. See, are you comfortable with this equation where we have by Kepler's laws and applying them to circular motion, the third law, we came to this conclusion. So here is mass times acceleration for the planet. Yeah, and the acceleration has been written for circular motion, and we have written that v squared as the circumference squared divided by the time period squared. Yeah. Now that me that appears here is the inertial mass of the planet, because that is what comes in the Newton's law ma, mass times acceleration. Are you okay with that much?
Yes.
Yeah. Okay. So now we are using Kepler's third law and saying that the square of the time period of revolution must be equal to the cube of the semi-major axis divided by Kepler's constant. Okay, so that is the use of K3, Kepler's third law. Now, but Kepler's third law says more. It says furthermore that K is independent of the planet, at least to some approximation. Yeah, so this is the key issue. Rearranging this formula putting it on the right hand side and solving for F. Yeah, so recall that F was over here. We get this formula for F. Are you okay with this formula for F? Maybe just rearrangement.
Yes.
Yeah. So let us look at this formula carefully. It is saying that the force, well, after you remove the R hats, I mean the coefficient of the force depends on the product of Kepler's constant and the inertial mass of the Earth. Okay. Now let us suppose we take Kepler's law very seriously and say K is independent of the planet. Then K has no dependence on ME. Are you willing to accept that?
On ME.
Yeah.
Okay, yeah.
Because it's independent of the planet. So it cannot depend on the inertial mass of the planet, nor can it depend on the color, composition, gas present, nothing. Yeah. So therefore, we conclude that this force is proportional to the inertial mass of the Earth. Yeah, because K cannot depend on ME. So in particular, it cannot be ME squared or any other such function of ME. Yeah, so it's proportional to ME. Yeah. Now there is the catch. It is not really true that K is independent of the planet. K has some weak dependence on planet. It is not the same for Mars as it is for Jupiter. It's not the same as Venus as it is for Jupiter. Yeah. So if we take that seriously, then we have to say that, K is not really, K may depend on the planet. And let us say that it depends on the planet through some property, which we will call the gravitational mass. So we will replace this KME by some new constant times gravitational mass of the Earth. Okay, so this is where I'm, maybe this is where you lost me. If K depends on planet, then that dependence will be encoded as some, so we will write K as some, or let me write even KME, because ME is anyway some property of the planet. This combination we will write as some small k times M gravitational of Earth. Okay. It is some property. I'm not saying it is some weight or something. Yeah, it is simply some property. We have just said that this K depends on the planet. Let us write that dependence in this way, through some parameter, which for our sake, our fun, we simply call it gravitational mass. Okay. Are you okay with this formula now? Where now this small k is now independent of the planet.
Yeah. No, so but I didn't fully understand, like previously when you discussed gravitational mass and inertial mass.
Yeah.
We talked about how you observe that they are proportional, and then you conclude that they differ only up to a constant or something, right?
Yes.
I didn't fully understand how we are defining gravitational mass. I mean, I see that in the equation, but
we are doing this here. So, okay, your confusion or your concern is well accepted. My presentation has been a little bit not in the order of historical events, not completely. Okay, I mean, the history is a bit complicated. So this should have come first. This discussion should have come first. In other words, the concept of gravitational mass really enters through the force between planets. It has to come from some kind of gravitational force. And this is the first time we are actually discussing that. So this should have come first. Now, so please put aside our previous discussion of gravitational and inertial masses for now. We'll bring that back. That is very useful. We'll bring it back. For now, we just make the observation that if Kepler's constant is not an absolute constant and has some dependence on the planet, that dependence could be encoded in some factor which we will call the gravitational mass. Now we will continue our argument going forward. We will say this f of r is equal to some 4 pi small k gravitational mass of Earth divided by r squared. Now we will impose Newton's third law, feeling that if the force of the sun on the Earth is proportional to some property of the Earth, then the force of the Earth on the sun should be proportional to that property of the sun. Okay. So based on that kind of argument, we will then conclude that f of r must really have a new expression 4 pi K prime MSG MEG divided by R squared. Okay. This step, is it okay, or should I go over it once again?
No, sir. I think
This is okay?
Yeah.
All right, great. All right, great. Where now K prime is now an absolute constant. It is independent of mass, independent of any property of the sun, and independent of any property of the earth. It is some absolute constant, and we call this 4 pi K prime in honor of Newton by G. Okay. Yeah, so sometimes called G Newton. That is how we come to Newton's law of gravitation. So this is Newton's law of gravitation, where I have really to write that the force is equal to minus G Newton ms gravitational m earth gravitational over r squared r hat. Okay, what I wrote previously was a short notation with suppressing important features. So no wonder I confused you. Okay, so this is really Newton's law of gravitation. Nothing else can be accepted. Yeah. Now we have to look at Newton's law of gravitation in conjunction with Newton's law of second law of motion, m inertial times acceleration, and do further experimentation to see whether this inertial mass and this gravitational mass of the same body are same, different, and so on. So that is where that other discussion came in. That should have come after this.
Yeah. Thank you.
Okay, you are most welcome. So is Shubham also at least partly satisfied? If he's here?
Yes, I mean, I got that.
Okay, all right. All right, thank you. Yeah, regarding your other point about elegant geometrical solutions of Newton's equation of motion for planets around sun and so on. Yeah, I mean, it is definitely true that Newton himself used largely geometric approaches, and as you pointed out, Feynman had a nice argument as well. But one has to remember what one is doing. See, it is one thing to find the shape of an orbit and say it is an ellipse or a hyperbola or any other curve. It is a whole other thing to know at what rate a planet traverses a particular geometrically shaped orbit, right? That is, what is the time dependence of the particle's position along that curve. That has tremendous physical information beyond purely geometric shapes. I mean, is it moving fast here, slow there? What is the functional form of R of t? Yeah, it is not so straightforward to get such things through purely geometric arguments. Yeah, so one, I would like to point out that with the passage of time from Newton to the next generation, which is basically Bernoulli's and Euler, they really put importance on the differential equation and derived detailed time dependence information, which I don't believe is so easy to get through purely geometric arguments, though one can do a lot that way. And yeah, so this distinction between the shape of a trajectory and the time dependence along the trajectory, I want to make that distinction.
Yes, sir. I was just like pointing out for that special case that there was a good solution. I just wanted to point.
Yes, yeah, yes. Your suggestion is an excellent one, and yeah, certainly well accepted. Okay, fine. Okay, so on this note, let us now let us now halt our discussion of. By the way, last time towards the end, I talked a little bit about perturbation theory and all. If you didn't follow, you're not alone. Please don't worry about it. It is just for general enrichment. You're not expected to have followed all of that. Yeah, and for curiosity for some later stage. Okay. If there aren't any other questions at this stage, I want to move to another topic. During this lecture, we shall briefly discuss. We've been talking about frames that move uniformly relative to each other. What if two frames are in relative acceleration? So the simplest possibility is two frames which are in uniform relative acceleration. Yeah, so this is called uniformly accelerating systems. So just a few remarks about this. So having dealt with frames moving at a constant velocity with respect to an inertial frame, we now progress to the nature of dynamics as observed from a frame S prime that is uniformly accelerating at the rate capital A relative to an inertial frame S. Okay, so this is the story. You have an inertial frame S and another frame S prime, yeah, which is accelerating at some rate A. Okay, so so the origin of S prime, yeah, is not, so the origin of S prime, so let me call that vector, let me call that vector S prime. This is the origin of the vector S prime. So that would be S prime minus S. If okay, no, I'm doing this in a poor way. So the origin would be given by there is some velocity which depends on time times t plus acceleration times t squared upon 2, plus of course some initial location. Yeah, so the main thing is that the difference between the two origins is not simply given by v times t, where v is relative velocity, but also an additional term. Yeah, where a is equal to v dot. Yeah, okay. V dot is a constant here. Okay, so now the acceleration of a particle in S prime is related to that in S by the following formula: A prime is equal to small a prime is equal to small a minus capital A. Okay, so this is the first thing to understand. As viewed in S prime, the acceleration is A prime. As viewed in S, the acceleration is A. The two differ by this capital A. Yeah, I mean, in particular, if the acceleration capital A matched that of the particle, yeah, then in that moving frame, you would say the particle does not accelerate at all. Okay. All right. So now let us look at the analog of Newton's law in this moving frame S prime, this accelerated, uniformly accelerated frame S prime. Now, what does it say? Yeah. So let's take the viewpoint that we first look at ma prime. So that is mass times acceleration. In by the way, here, just to be clear, these m's are all inertial masses. Yeah, so the matter will come up once again. But I will not make that distinction right now. So this is mass times A prime. We will call that the apparent force in the primed system. Now, since A prime is equal to A minus capital A, I can rewrite this as M small a minus M capital A. Now, since Newton's law holds in the original frame S, which is inertial, we can replace M small a by whatever forces were acting. Okay. So from this, we conclude that the force, apparent force as seen in S prime, is not the original force, but is shifted by inertial mass of the particle times the acceleration of the frame. All right. So this is the first conclusion, first important observation. S prime is not inertial. S is inertial. In particular, Newton's second law does not take the same form in S prime as it did in S. Because it's, I mean, if it did, it would simply say that ma prime is equal to force. Yeah, but that is not true. There is some additional term. Yeah. We have, of course, assumed that the masses of the particle are the same in both frames. So that is part of the assumption. Okay, so then, so unlike in a frame that moves uniformly, the force seen in a non-inertial frame, S prime is not inertial, we call it a non-inertial frame, is generally not the same as in an inertial frame. Yeah. The apparent force in S prime may be expressed as F prime is equal to the original force plus what we call a fictitious force. This term we will call the fictitious force, where the fictitious force is given by F fictitious is equal to M minus M times capital A. Okay, we are assuming that capital A is a constant acceleration. Yeah, I mean, that is the case we are discussing here. So notice that this fictitious force points oppositely to the direction of acceleration of the frame. Okay. Now let us make further remarks about this fictitious force. Notice also that this fictitious force on the particle is uniform. It is independent of the location of the particle within this frame S prime. Okay. This frame is moving, in fact, accelerating. Now, whether the particle is here, there, everywhere, the fictitious force is one and the same. It only depends on the acceleration of the frame, not on the location of the particle. That is the point being made. Independent of location, but it is proportional to the particle's mass. Yeah, so these are the two features I want to highlight, that the fictitious force points in the direction opposite to the acceleration of the frame, is independent of location, and is proportional to the particle's mass, here inertial mass. Okay. Now, these statements sound a bit familiar. In fact, this is just like the gravitational force on a massive particle on the Earth's surface, right? Think of a particle above the Earth's surface nearby. The force that it feels is proportional to its mass. Well, in that case, gravitational mass. It's also uniform. No matter where I am located, the force is the same. It is m times acceleration due to gravity. So in that sense, it reminds us a little bit about gravity. That is, a uniformly accelerated frame involves a fictitious force that looks a little bit like gravitational force. We're going to elaborate on this in a moment. However, the fictitious force arises from the acceleration of the frame. Yeah, those were the similarities, now the differences. It arises from the acceleration of the frame rather than from interactions between particles. Okay, so that is an apparent difference between the two, and for that reason, we give it the name fictitious force. So that's just the reason for the name. But now we are going to look at it in a little bit more detail, the similarity between this fictitious force felt by a particle in an accelerated, uniformly accelerated frame. Yeah, let us first look at it through an example. Okay, any question about what we have written so far? Okay. If not, yes, please.
Sir, about the similarity of fictitious force and that gravitational force, I mean, doesn't the gravitational force by Earth point in the direction of the acceleration due to gravity?
Yes, definitely. Definitely. Yeah. We are working in an approximation. The Earth is flat and the acceleration due to gravity simply points downwards. Yeah, so we are working in a local region. So that's very important. We are looking in a very small laboratory where the curvature of the Earth can be safely ignored, and gravity points purely downwards towards my floor and parallel to my wall. Right? So it is within that local approximation. So we are comparing fictitious force due to in a accelerated frame, uniformly accelerated frame with a uniform gravitational field.
Yes, sir. My doubt was regarding that only. Like the fictitious force points opposite to the acceleration.
Yeah, of the frame. Indeed.
But like the gravitational force, it is in the direction of the acceleration.
Okay. No, so you have to choose. So to make the analogy, you have to choose the acceleration due to gravity to point as a minus a. Okay, so you have to. That is the correspondence. Is that what you are saying?
I mean, like I was you said it sounds bit. You pointed out that this fictitious force sounds bit like the gravitational force.
Yeah.
But the fictitious force is opposite to the acceleration, whereas the gravitational force is in the direction of the acceleration. I mean,
okay. So yeah, there is that difference if you want to view it that way, and yeah. So there is a, I mean, there is a sign difference, so to speak. So we have to think of it in this manner. Yeah. So that is accepted. Yeah. I mean, the all I was saying is that they are similar insofar as two features are concerned, that they are both proportional to the mass. Well, even there is a bit of an issue. One is proportional to gravitational mass, one is proportional to inertial mass. So there is a vague similarity. And the second similarity is independent of location. If it's a uniform gravitational field, no matter whether I'm in this room or the neighboring room, it's the same gravitational force. Same way, no matter where I am in that frame.
Okay, sir. So like you're talking about only these two features.
Exactly, these two features. Yes.
Okay.
Yeah. Yeah, and the reversal of direction has to be part of the correspondence. We have to accept that as part of the correspondence. I mean, we are giving a map between two situations, so you have to define the map within the context of that map. You can say they look similar. And the map or the rule is to reverse the sign. That is part of what you're supposed to do. Okay, so now let me look at an example, a very simple example, a traditional and well-known example as well. So let us look at the fictitious force in an accelerating car traveling on a road. Yeah, I mean, the road is straight, the acceleration is uniform. Yeah, so the car is not turning and so on. Yeah. Now let us suppose that within the car, a small bob of mass m is suspended by a string from the roof of the car, and that the car accelerates at the rate a. So here is, let me draw my car as a little box, and here this is the road. The car is accelerating in this direction at the rate a, and there is a pendulum bob that is hung from the roof of the car. Now we can view this situation from two interesting frames. From two interesting frames. Okay, there is a question from Romit Raj Chaudhary. A is the acceleration of the frame.
That was a reply to Shubham, not a question.
Sorry. Could you repeat what you said, Rupa?
That was a reply to Shubham, not a question. Just doesn't.
Oh, okay. Okay. All right. So is this something I should go through, or okay, let me just read what you say. A is the acceleration of frame with respect to an inertial frame, though. In the case of gravity, the acceleration due to gravity is not the acceleration of the frame itself. We could consider the flat pizza Earth hurtling humans first into space, maybe. Okay, I will leave. Okay, there are distinctions in a sense. Okay, coming back to this really nice little example. Here is my car. I want to view it from two frames. The car frame. By the way, is the car frame inertial? And the second frame is the road frame. Okay, so please tell me which of these is inertial, or at least to some approximation.
Road frame.
Yeah, so the road frame is an inertial frame. Yeah, so for many purposes, the Earth is, we are going to ignore the effects of the rotation of the Earth and so on. So within that context, the road frame will be regarded as inertial. Now the car frame is an accelerated frame. So that is a non-inertial frame. Yeah, in particular, a free particle in a non-inertial frame will not necessarily follow a straight line trajectory at constant speed. So that is, yeah. Now let us look at this in more detail. The situation is viewed from the inertial frame of the road as well as from the accelerated frame of the car. So let us look at each one separately. Viewed from either frame, what is experimentally seen is that the string is seen to settle into a configuration where it hangs at a non-zero angle relative to the vertical, with the bob displaced towards the back of the car. So I hope this is reasonable. If you do it in a car, you will notice this. It is seen to be displaced from the vertical and hang sort of backwards. And the angle that the string makes with the vertical as well as the tension in the string are found to be the same in both frames. So this is what a pair of experimenters tell you, and we are just going to analyze the situation briefly. Now this angle, it turns out, is given, or rather the tangent of the angle is given by the quotient of the acceleration magnitude by acceleration due to gravity, while the tension in the string, so the tension of the string is the force in the string that is sort of pulling the bob, and that is given by the mass times square root of g squared plus a squared. Yeah, I mean, this has the dimensions of force. This is a mass and this is an acceleration, or the square root of the square of an acceleration. So this definitely has dimensions of force. Yeah. Okay, so let us see where these two formulae come from. That's fairly straightforward. So let us obtain these results in two ways. On the one hand, by working in the inertial frame of the road, and on the other hand, in the accelerated frame of the car. Okay, so what do we see in these two frames? Well, let us first look at the inertial frame of the road. In that frame, the bob is not at rest. It is being accelerated, and I mean, it is at rest relative to the car. Yeah, it has eventually come to rest relative to the car, but the car itself is being accelerated. So the bob also feels some acceleration, and that is given by A. Now, what are the forces on the bob? Well, there is some tension force in the string, and there is the force of gravity. These are the two forces. Now, the vertical tension force, vertically upward tension force, and the vertically downward gravitational force must be balanced, because those are the only forces there, and the bob is not going up and down. Yeah, so there is no vertical acceleration, no vertical acceleration, only a horizontal acceleration. Yeah, and therefore we can equate mg with t times the sine of theta. Yeah, so mg is equal to t sine theta. While on the other hand, so okay, let me continue where I was. So for instance, in the accelerated frame, namely the frame, oh my goodness, I'm doing the other one first. Okay, so let me go there. Okay, in the rolled frame, the bob accelerates. Yeah, I'm sorry about that. I've reversed the two. Let's go back to the road frame. In the road frame, which is the inertial frame, the bob accelerates in the direction of motion of the car, and the vertical component of the string tension is balanced by the weight of the bob. Okay, so that was the equation I wrote here. Mg is equal to t sine theta. And the other one equation is going to say that, oh, I'm sorry, this is t cosine theta. Very bad, sorry. And t sine theta must equal mass times acceleration. These are the two vertical and horizontal Newton equations in the inertial frame. So taking the ratio of the two, we get that the tangent of theta is equal to, that is, I divide the second equation by the first, I will get tangent of theta is equal to A upon G. Tangent of theta is A upon G. Okay, so that's how you derive that formula. The other formula, namely the formula for the tension itself, is got by squaring these two and adding them up. So you will get that t squared cos squared plus t squared sine squared is equal to m squared g squared plus m squared a squared, and cos squared plus sine squared is 1, and so you get this formula for the tension. So that is the analysis in the inertial frame. Now let us go to the car frame. The car frame, the bob is simply at rest. It is not accelerating relative to the car. Bob at rest, no acceleration, neither vertical nor horizontal, no acceleration, vertical or horizontal. However, being an accelerated frame, uniformly accelerated frame, there is a fictitious force present, and according to our recipe obtained previously, that fictitious force, F fictitious, is given by minus m times the acceleration of the frame. Okay, so this is the force diagram. There is still a tension in the rod or the string. There is still the vertically downward force of gravity, but now there is this fictitious force. So this is the Newton equation in the other frame, in the accelerated frame. So equating the components of T to the respective fictitious and gravitational forces, you get essentially the same equations. All right, so you will get that T cosine theta is this one, should be equal to mg, and T sine theta must be equal to ma. Okay, so these are the two equations you will get, and the same conclusions follow. It's this. So when I write m minus ma here and put a direction here, I hope you don't get confused by that. A is rightward directed, so minus a is leftward directed. Yeah, so the component in this direction has size ma, not minus ma. So any question about the way we analyze this simple problem in two frames? Okay, so now let us then proceed to the next concept in concerning uniform acceleration. This is the so-called principle of equivalence. We have met it in a different form earlier. Let me explain it through some examples here. So what we have seen that Newton's second law in a frame that accelerates uniformly at the rate a is the same as that in an inertial frame, provided we introduce a fictitious force F equal to minus ma on each particle in the accelerated frame. Right. So this is our main conclusion. If you want to do physics in an accelerated frame, simply introduce a fictitious force and then use the same Newton's laws. And that fictitious force in a uniformly accelerated frame is simply minus ma on each particle, where a is the acceleration of the frame. That is the recipe. Okay, now some comments about this fictitious force. The fictitious force is indistinguishable from the gravitational force due to a uniform acceleration due to gravity given by g equal to minus a. Okay, so this is part of the recipe. You have to take g is minus a. Now, okay, in saying this, I have to be careful. When I say it's indistinguishable, provided you suppose that the gravitational mass that appears in the force due to gravity and the inertial mass that appears in Newton's law, which was here, are assumed to be the same. So that assumption is going in, and we will comment about that. That is part of the principle of equivalence. I have not stated it explicitly here. I should have. So both forces are proportional to respective masses of the particle. Yeah. Now, this is the matter that Einstein was thinking about. So Einstein posed the question of whether the two are distinguishable even in principle. Yeah, I mean, the way I have written it is somewhat circular. I am saying it is indistinguishable, but so we're just going to think about it a little bit more, that's all. Yeah. So he's just going to discuss the same thing in a few examples. So for instance, in an inertial frame in which a local gravitational field is present with constant acceleration due to gravity g, a free particle of mass m is subject to a force F equal to mg. Okay, so and we want to compare these two situations, namely a force on a particle due to a uniform gravitational field on the one hand, and the force that a particle fictitiously feels because the frame itself is accelerated. Yeah, so these two situations, we are just going to compare them a little bit. Yeah, we already noticed that they are very similar when appropriately transformed, namely by taking g as minus a. So now suppose a particle is isolated far from all physical interactions, okay, so that we can call it a free particle, and it is observed in a frame that is uniformly accelerated at the rate a equal to minus g. Then in this frame, the particle is subject to a fictitious force minus ma, which is also equal to mg. Okay. Einstein asked whether it is possible for an observer in either of these two frames, namely the previous one I talked about, where there's a uniform gravitational field present. Yeah, so there are forces present over there, real forces present. And the second situation where a particle has been taken far away into outer space, but is being observed from an accelerating frame over there, with the acceleration of the frame chosen to be minus of g of the previous discussion. Yeah, whether it is possible for an observer in either of these frames to physically distinguish between these two situations. Okay. So basically he said it's not possible to distinguish now, but he had a few thought experiments to discuss some aspects of this matter. So to make the question more concrete, he proposed the following thought experiment, and thought experiment in German is called a Gedanken experiment. So that is the name given. Yeah. So let us suppose a man is on an elevator at rest in a uniform gravitational field. So that is like above the Earth's surface. There's an elevator. So the gravitational field has magnitude g. It points downwards, of course. Now, if the person releases the ball from rest, then, I mean, the elevator is not moving just yet. Okay. Then, oops, 1 second. Then the ball, if he releases the ball from rest, then it falls downward with an acceleration a equal to g. So this is, you don't even call it an elevator, you can just call it a room. But so it's not moving relative to the Earth. Yeah, if a person releases a ball, it falls, it is seen to fall down with this acceleration. On the other hand, suppose this same elevator is far from other physical interactions, far from the Earth, and in outer space, it simply accelerates upward at the rate a equal to g. Yeah. Now, if the man releases the same ball in the same manner in this accelerating elevator, it again accelerates downward at the rate g. Yeah. That's because there is a fictitious force pointing that way and will cause, in effect, an acceleration downward. Okay. So as far as the man is concerned, the two situations are identical, and he has no way to tell whether the elevator was accelerating in outer space or the elevator was near the Earth. Okay. So this is the main assertion of Einstein, that a man in a closed elevator, by dropping a ball, cannot tell from the acceleration of the ball whether the acceleration is due to a gravitational field, uniform gravitational field, or because the elevator itself was accelerating in outer space. So just to make a parenthetical analogy, this may be regarded as a kind of 20th century version of Galileo's assertion from the 17th century that it is not possible to dynamically distinguish between an inertial frame and one that is moving at constant velocity relative to inertial frame. Okay? That is a ship at rest, it's in the dock, and a ship moving uniformly at sea. Yeah, Galileo said that you cannot distinguish these two by doing mechanical experiments inside a closed room inside the ship. Yeah, same way, Einstein is saying that you cannot distinguish these two situations. In fact, Einstein also proposes one more experiment, which is that of a freely falling elevator. This is also quite nice, so let me mention it. So another way to look at the equivalence between a uniform gravitational field on the one hand and an accelerated frame is to consider an elevator that is now freely falling in a uniform gravitational field. So look at it this way. You have the Earth, you have an elevator. Now the elevator cable has unfortunately been cut, and that elevator cabin is falling freely in Earth's gravity. Okay, so let us see what things happen inside this elevator. Now the elevator, the man, and the ball all accelerate downwards at the rate g. Okay, the whole thing is freely falling. Yeah, it's in a tall building, so it falls for some time, I hope. Yeah. So if the man releases a ball, what will it do, or what will the man perceive? Well, we will perceive that the ball simply remains suspended as though the elevator is motionless, far from other physical interactions. So even though the elevator is above the Earth, according to the man, he can't tell whether, what the man actually sees, let's go of the ball, but the ball simply remains there, doesn't fall. Yeah. And why is that? According to our discussion, the local gravitational field, which is downward and wants to accelerate the ball, is exactly cancelled by the downward acceleration of the elevator. See that? We are now in an accelerated frame. The elevator is accelerating. An accelerated frame, there is a fictitious force that points opposite to the direction of acceleration. So the force due to gravity, so this is a freely falling accelerated observer. Yeah. So there is anyway this mg force due to the earth, but there is also a fictitious force which is given by minus mg that is pointing upwards because the frame itself is accelerating. These two cancel each other out. Yeah, the local gravitational field is exactly cancelled by the downward acceleration of the elevator, and Einstein concluded that an observer in the elevator cannot determine whether the elevator is falling in a uniform gravitational field or the elevator is isolated in outer space. These two situations you cannot distinguish without looking out of the elevator. Yeah. So this is these are the comparisons that Einstein made and thereby formulated what is called the principle of equivalence. So let me just state that. So this is the idea of the principle of equivalence, which states that it is not possible to distinguish locally. Okay, the word locally is quite important. Yeah, over a large expanse of the earth, the acceleration due to gravity does not have a uniform direction. It points towards roughly the center of the earth. So due to the curvature of the earth, there will be changes from location to location. And even the magnitude itself may change a bit. Yeah, because the earth is not perfectly spherical and so on. So so that it's not possible to distinguish locally. When locally also means without looking out of the elevator and doing such things, or making phone call to somebody else and asking, is my elevator falling? Such things. Yeah. So distinguish locally between a uniform gravitational field with acceleration g, observed from an elevator that is at rest or moving uniformly. Yeah. And on the other hand, a coordinate system or elevator that accelerates at the rate a equal to minus g. So these two situations are indistinguishable. Yeah. The restriction to local is to avoid inhomogeneities in real gravitational fields over large enough distances. Yeah, and to avoid situations where the person actually looks out of the elevator. So this is the principle of equivalence. But as I said, implicit in our discussion has been the assumption that the mass of the ball that appears in the inertial term ma in Newton's second law is the same as the mass that appears in the formula for the gravitational force, which is mgr times g. So making this analogy, we assume the two are the same. So part of the principle of equivalence is also the assertion that the inertial and gravitational masses of the ball or of any body are numerically equal, min equal to mgr. Okay, so this is the principle of equivalence. It has these two things built in, that inertial and gravitational masses are the same, and a uniform gravitational field is indistinguishable from uniformly accelerated frame of reference going in the opposite direction. Okay, so this is a brief discussion of accelerated frames. There are other types of accelerated frames that are very interesting. For instance, a rotating frame. Yeah, the earth itself is rotating, so that is also an accelerated frame, or a rigid body that is rotating, a spinning top, and so on. So those are also, if you go to a frame that is fixed in the top, that is no longer an inertial frame, and one would like to see how physics looks in such a frame. I'm not discussing that over here because of some shortage of time, but I thought at least we should have the idea of uniform acceleration and how it's related to the equivalence principle. Okay, so please go over these two Gadankan experiments slowly and convince yourself about what has been said. It is a fairly simple idea, in fact. But any questions at this point before we stop?
So,
Yes, Romit.
so this is a slightly nonsensical, but I don't see why it's significant that the fact that a uniform field force looks like a fake uniform field force. I mean, gravity is a uniform force that acts on every object in the same with the same
okay. Okay, so maybe the significance of what, okay, we have made an observation that two physical situations are very similar. Uniform gravitational fields look a lot like physics in uniform gravitational fields looks a lot like physics in uniformly accelerated frames. Okay. Now, why is this important? It is because that if you want to now understand gravity, maybe you should not go trying to study gravity. Maybe you should study motion in accelerated frames. So that is the insight that Einstein has, that maybe gravity is to be regarded as some kind of study of motion in accelerated frames. And that is the viewpoint that he then championed and developed his theory of relativity, general relativity. Okay, so the significance of what we have just discussed is really there. If that is the sort of, I mean, you ask something, but this is where it is useful, that to understand gravity, you should study motion of accelerated observers, first of all, uniformly accelerated observers. Yeah, so that is the message that Einstein is giving. That gravity is really like some kind of acceleration in some colloquial terms. So Romit, is that?
Yes, I think so. So the idea is like, is that it behaves the same way, right? It's not fundamentally the sort of.
Yeah.
I hope not. All right. Maybe it's better not to know. I think that answers.
No. See, the question is that if by no physical experiment you can distinguish the two, then in what sense we can say they are different? Yeah. So one is trying to take that very seriously. Yeah. So okay. So if two physical situations cannot be distinguished by a certain class of experiments or observations, then the dynamics that ensue in those two situations maybe can be described in a similar way. Yeah, that is the insight that is being arrived at from here. Yeah.
Yes, that's all right. Thank you.
Okay, fine. Any other?
Sir, I had a doubt.
Okay, sure.
Sir, like we here came to the conclusion that motion in uniform accelerated frames are similar to uniform gravitational field.
Motion in uniform
gravitational.
Yeah.
So, but like if we consider a frame which is moving with uniform acceleration due in a electric field, I mean due to an presence of an electric field, the frame is being accelerated at uniform acceleration A. In such a frame, if we take an electron and a proton, because the charges are opposite, they'll respond opposite to the direction of field. But if we like take it in, if there's a gravitational field present and this acceleration is being caused by gravitational field, the difference between electron and proton will not be there. I mean, if we disregard the masses of electron and proton, just assume that mass of electron is equal to mass of proton. So we are able to distinguish between these two cases. So like I don't see how here.
Yeah. Okay, I didn't quite catch the import of your question, but okay. No, I mean, the electric field couples to particles through their charge, whereas the gravitational field couples through the gravitational mass. So these are different. And that is true. That is true. We do accept that.
Sir, but by doing physical experiments in these two cases, we are able to determine there's an electric field present and an electric field is not present. I mean, we are not in a gravitational field.
Okay. So you were saying that the acceleration of the frame. No, see, okay, I lost you a little bit. What are the two experiments you're performing, or two situations?
Okay, sir. We are in a frame.
Yes.
In which is being accelerated by a uniform electric field. I mean, because and the second case is with same acceleration, we are being accelerated by the gravitational field. Now, in these two cases, with that experiment of electron and proton, we are able to distinguish that this is not a gravitational field. We are not in a gravitational field, and we are doing this experiment locally, not looking outside.
Okay, maybe okay. So all right. Perhaps okay, I should think about your or even understand the formulation of your question more carefully. It is possible that what you are suggesting does not
I think I can sort of
not very clear about okay, let me think about what you have said, or if you could formulate it more clearly, I will understand better.
Sir, I think what he means is that even if there is a force like that is causing some kind of acceleration, you can rule out the fact that you can conclude that that it isn't actually gravity. And the example that he gave was if there is an electric field, right? And whether the particle is a proton or a negatively charged particle of the same mass, you can actually conclude that it isn't gravity, but a different force that's causing that acceleration. Is that right, Shubham? Like,
okay,
what you meant?
Exactly. This was my point. I mean, we could conclude that with this experiment with proton and maybe electron.
I think that may be going slightly outside the purview of what was said, because all we said is that there is an accelerated frame and there is a fictitious force that is proportional to the mass and in direction opposite to the acceleration. Now, if your setup somehow goes beyond this, then we cannot come to the same conclusions.
The setup does not go beyond that. I mean, there's nothing being said about how this fictitious acceleration is being caused. So I just
say something.
One thing.
Like you're saying that the frame is being accelerated by a field, but how can a frame be accelerated by a field? Like either the body is being accelerated by the field and the frame is attached to the body.
Okay, like the body is being accelerated and we are in the body and that is our frame.
Yes, but then the force doesn't act the same way, right? Because the force on the other objects is still determined by their charge and not their mass. So the force is mathematically not the same. So like, I mean, you're thinking of three cases: an electric field, an accelerating body, and a gravitational field, in which case the gravitational field is at rest. Now, if you consider an electric field, either it's an accelerating a body accelerating in an electric field, in which case there's two separate field forces, the fictional force and the electric force, which does not depend on mass, or it's a body which is stationary in an electric field, in which case, I mean, I just considered all of the examples because I thought they were getting sort of clashed into each other a bit, but you get what I mean? Doesn't make sense.
Yeah. Okay. I must admit I am still not very clear about the setup and what exactly is meant by the frame and how the electric field entered that.
So maybe I'll formulate it a bit better and mail to you.
Sure. Yeah. Perhaps that would help. Yeah. You can think about. Yeah.
Romit's point, I lost you in between.
Okay.
I think I lost myself too.
Okay, fine. Yeah, one has to be careful in saying what you mean by a frame and what role this electric field went into in defining the frame. I was a little confused about, but perhaps one can resurrect what you said. Okay, any question other than this? Otherwise, we will continue on Thursday. Yeah. All right. In that case, let us halt here. Have a good afternoon, and let us meet again on Thursday.